We started section 3.2 last time, and we're taking a look at addition of whole numbers. We talked about sort of the basics of what that looks like, and done a couple of models for addition, and then we stopped. So we're going to look at a little bit more terminology and some properties, and then we're going to look at some algorithms as well. So the phrase less than means the following. So for any whole numbers A and B, A is less than B, written with the less than symbol, if and only if there exists a natural number K such that A plus K is equal to B. So what it means for 1 to be less than 2, we'll use 3 even, 1 less than 3, is that there's some number that I can add to 1 to get 3, and that blank spot has to be a natural number. So it can't be 0, it can't be negative, it can't be fractions, decimals, etc. It has to be a natural or a counting number. So there's some number in here, it's R2, right, that I can add to 1 and I can get to 3. That's the definition for less than. So using that idea, we're going to do the same thing, but we're going to talk about what it means if I talk about subtraction within the definition. So it says to give a definition of less than, but to do it with the phrase with an equation in it that it uses subtraction instead of using addition. Okay? Most of what we're going to write is going to be copied directly from the other statement. So it starts out saying for any whole numbers A and B, A is less than B, written A less than B. We're going to start out saying the exact same thing. Okay? So you're just copying down the first phraseology of the previous definition. So for any whole numbers A and B, A is less than B, which is written in symbols like this. And then the next part says if and only if, so we're still tracking along with doing the same thing. There exists a natural number K, all that's the same. Such that, okay, the only thing that's going to change is that my previous statement about addition has to be a statement about subtraction. So instead of writing A plus K is equal to B, how could I write this statement in subtraction? No. B minus K. Okay? So in essence, if you think about from an algebra standpoint, right, we can shift the subtraction of K to the other side. I don't think that's the best way to think about it, but it is one way to think about it. I think what makes more sense to talk about is my example where I did 1 and 3. If 1 is less than 3, I can add 2 to 1 to get an equal statement between them. Or what could I do to the 3? Well, I could subtract the 2 from the 3. And what this does is it creates something that is utilized a lot in schools. They're called factor families, okay? They're not always called factor families. That's not what they're called, because that's with multiplication and division. There's another name for it with addition and subtraction. But there's a name that talks about how these are all related, and they do them in groupings together to emphasize that there's this natural relationship that's happening between all of them. Okay, so we have these groups of numbers. We can actually either add a 2 on one side, or we could subtract the 2 from the other side, and we're going to get a statement that's equal. So this is a definition using subtraction. What you're going to have in your homework or group, I don't remember which, is a statement asking you to do the same thing, but to define it for greater than. Again, a lot of the terminology is going to be the same. The parts that are going to change are the parts where we said less than, and this symbol less than. And obviously your equation at the end, whether you're using addition or subtraction, is going to be different. Okay, so that's something to sort of prep your mind that you're going to be thinking about. There are 4 whole number properties that we're going to look at. The first one always throws people, okay? It's called the closure property. The premise for it is very straightforward. It says that if you have 2 whole numbers and you add them together, you get a whole number. Okay, so those of you who are still working on your test redos and you're doing the Gauss problems, you're supposed to be adding a whole bunch of whole numbers together, and some of you are getting decimals. That can't happen. It means there's an error in some of the things you're doing, right? If you add whole numbers together, you have to get a whole number. Now, that's the closure property for whole numbers, but it's the closure property for anything. So if you take a certain grouping of numbers that's smaller than whole numbers, like let's just say you take even numbers. If you add even numbers together, will you get an even number?
Yes.
Yes, you will. It works all the time. But what if you do odd? Oh, so if you add two odd numbers together, you don't get an odd one, right?
You can get an even.
You get an even. So closure happens when you get the same type of number you already had. So whole numbers have closure. Even numbers have closure, but odd numbers don't. Odd numbers don't have closure because odd plus odd is not odd. Is everybody with me on that? That's what it means for closure. Okay, think about what happens if we were to do, and we will do this later. This is specifically talking about addition, but there's nothing that relegates this description to addition. It could be talking about multiplication or division or subtraction. If I add two whole numbers together, I get a whole number. What happens if I subtract two whole numbers? What's that? Sometimes. Sometimes.
You get a negative number.
You could get a negative number. Can you give me an example, RJ?
-2.
Okay, I mean two numbers that subtract to give me -2.
Oh, 4 minus 6.
4 minus 6, perfect example. So if I take 4 minus 6, I actually subtract that and I get a negative. So this property, and we'll see this again in subtraction, doesn't hold for subtraction, right? I do not have closure for subtraction with whole numbers. So it's both based on the property, this is addition, and it's based on the type of number. So we've seen it fail for the type of number being messed up, right? Odd plus odd is not odd. And we've seen it for the type of property or operation being subtraction not working. So it both matters the operation that we're using and the types of numbers that we're using. So what your book's going to do is going to give you some lists of numbers, and it's going to ask you the same question. Are these closed? And the question you keep having to ask yourself is, if I add any of these numbers to together, do I still get a group that's a number that's in this group? That's the question it's asking. And it's specifically going to do it with addition because we're working with addition in this section. And we'll see some subtraction and other things later. Commutative. The commutative property is one where I will tell you right now, I will take off if you don't spell this right. Because usually when people mess this word up, they turn it into another word that's a real word. And they'll say something like commutative or communicative or something like that. We throw extra letters in, we take some letters out or whatever. Commutative is like the word commute. Right? So you see people or hear about people commuting to work, right? Or maybe you even commute to school. So commute means you're going from one place to another place and back and forth, right? It's this round trip process that we do. I commute to school every day, okay? So when we're looking at this commutative property, it's telling you that the order doesn't matter. So A plus B is equal to B plus A. And we're very grateful that this is true because it makes learning addition and some of our other facts later as well a lot easier. Because if a child already knows that 3 plus 7 is 10, then when they get to the plus 10, plus 7s, right, all the ones that are 7 plus something, they don't have to relearn what is 7 plus 3 because they already know it, right? So a lot of times kids will start out learning, what happens when I add 0 to everything? What happens when I add 1 to everything, right? Well, I don't care if I get to plus 7s because by the time I get to plus 7s, I've almost learned all those already because it's a commutative property. Associative property. So the word associative is much like you talk about when you talk about who you associate with, right? And we represent this by some grouping symbols, which for us most of the time is parentheses. So it talks about the fact that the grouping of the numbers does not change the result. So if I add A and B and then I add C, I get the same thing as if I add B and C grouped together and then I add the A. Okay, so the grouping, the association for addition doesn't make any difference. I get the same list of numbers. And again, that's a very friendly feature because sometimes in a list of numbers, there are certain numbers that add together easier than others. Like you might have a list of numbers and you have a 2 and an 8 in it. Well, 2 and 8 are very nice to add together because you get 10, right? But like 8 and 5 or 8 and 12 or 8 and 8 and 12 is not a good example. 8 and 13 are not very nice because you don't get a nice number when you're adding them together. So being able to regroup and add things that are easy to get to group together first is sometimes an easier problem. And the last one is the identity property, and I'd like for you to write in the word additive here. I realize that we're working with addition, but there are going to be two identity properties, and they are different. This is the additive identity property. So if you're identifying that you're using an identity property, you need to say which of the identity properties you're using. Here, we're talking about additive. The additive identity property says there is a number that you can add to things and it doesn't change their value. That number is 0. So we call that number 0 the additive identity. It is the number that we add to things and the value doesn't change. And it doesn't matter the order in which you add them, right? Because things are commutative. So a plus 0 is the same as 0 plus a. And so since we have that property, the order doesn't matter when I add the identity to the numbers either. So what I'd like for you to do then is you've got example 3 here with 4 problems. And this is not like, a test bank where you mark things off. There might be duplicates. Something might not be included. Okay, so just beware of that. There are 4 questions, and I'd like for you to decide in each case, which property do you see being used? And once you've written down your 4 responses, I'd like for you to turn to a neighbor and see if your choices match. Do you think it's the same one? Okay, what do you think the first one is? I agree, it is the commutative property, yeah. And we're all making sure we're spelling it right?
So what's the difference
of course.
between that and community?
That's community. It has to do with being in a community.
So all my life I've been saying that.
It's very possible. There are people who say words wrong their entire lives. Yes. How about the second one? What do you think? That's the additive identity. If you didn't write or additive, go ahead and add that back in. Additive identity. I know right now it's the only one we have, but we will have another one shortly. How about the third one?
Commutative.
It is the commutative property, yes. So over here, Tess, I heard you describing what about this made you know for sure it was commutative as opposed to associative? Because there's parentheses in it, right? So if you made a mistake, you might have written associative on this one. What do you think?
The 2 didn't move, just like the 8 and the 6 flipped on the second half.
Yeah.
And so it looked like commutative.
Yeah, so she noticed first that the 2 didn't move. You might also notice that the parentheses didn't shift, right? That's another thing you could notice, right? Or you could notice that the numbers that are within the parentheses are the same numbers from one to the other. Lots of sort of red flags, but there are parentheses there. And the fourth one, that's associative. We've got the associative property. All right. There are some basic addition strategies, and you may have used these, you may not have. Kiki?
So is closure property over all of those 3?
So closure property, when they write it out, looks something like this. They'll say something like 2 plus 3 is an element of the whole numbers. That's what the closure property would look like if they were giving an example of one. They're talking about what kind of a group it's still in when you add them together. Yep, good question. All right, so some of these strategies you may have seen. I mean, undoubtedly you will have, but some of them you might be looking at and going, I don't remember ever learning that. That's quite possible. Some of these strategies have come about since you were in, kindergarten, first grade, learning them. And that doesn't mean you have to love them, but you don't know what kind of curriculum you might be teaching if and when you should teach something. And so I want to make sure you're seeing some of the things that are present even now. So counting on is one that I know that I used when I was little. It's a pretty old one. So the counting on strategy is you start with one value and you count up the additional amount of the other value. So this is what kids do a lot of times when they're counting on their fingers too. Like you don't have to be doing it on your fingers for this to be the strategy. But the counting on strategy is something like this. You start with 5 plus 3 and you say, I've already got 5, and then you go 6, 7, 8, right? You count 3 more up from there. Doubles is a relatively new one. It's definitely not as old as the counting on addition. But they're my children, I can't remember at what point I noticed it, at which child along the way, started doing this in school. And so instead of learning their like plus ones and their plus twos and their plus threes, the first thing they learned when they learned addition is they learned all their doubles. So they learned 1 plus 1 and 2 plus 2 and 3 plus 3 and 4 plus 4 and 5 plus 5 and so forth. Are you with me? So that's the place where they started memorizing first, right? So the reason, or the way that that's usable, is that if a student knows their doubles, that is that they know that 3 plus 3 is 6, then they can take something like 3 plus 4 and think of it as being I call it in my house when I'm working with my kids, a near double. That's just my terminology, because it's nearly a double, right? 3 plus 4 is pretty much 3 plus 3 and a little bit more. Well, how much more? 1 more. So if I know that 3 plus 3 is 6, then 3 plus 4 would be 1 more than 3 plus 3, so it's 7. Are you with me? Okay, that is a strategy that is definitely being used in curriculum right now. Another one is making 10. Another one that I've already mentioned this one actually today. So the idea of making 10 is instead of learning maybe that you've got all your additions that are doubles, you learn all the additions that add up to 10. So you learn that 1 plus 9 is 10, and 2 plus 8 is 10, and 3 plus 7 is 10, and 4 plus 6 is 10, and 5 plus 5 is 10. So you learn the make 10 pairs, right? The pairs that make 10. And so then when you're looking at a number like 8 plus 6, you think, well, what do I have that 8 would make 10 with? And the answer would be 2. I know that 8 plus 2 is 10. Well, 6 is 4 more, so I add those 4 on afterwards. So if a child were doing this, they wouldn't write this list down. I want you to understand that real quick. But this is the thinking that they would be going through, is that they would be thinking, oh, I'm just going to break this 6 down into 2 and 4 because I know this is 10 and I add 4 more. Are you with me? Okay, so this is another strategy. All right, what we're going to do next is we're going to actually take a look at what are called algorithms. So these are algorithms of addition. And again, the first one is going to be the one that's most commonly used and used beyond elementary school first off. I mean, it's the one that we continue to use. It's efficient. Okay, efficient means it's time valuable, right? Like it saves you time. So aside from like a calculator or whatever, it's a pretty efficient way to do it. And so that beckons to our sense of wanting things to get done and moved on from problems. So we kind of keep this one around. So this is, I'm sorry, it was the next one I want to do, standard algorithm. Let me do this one since I just talked about it. Okay, we'll do this and we'll go back to concrete. Okay, so the standard algorithm, the one that's efficient, says that I'm going to write the numbers in a vertical form. I'm going to start with the ones column, and I'm going to add 4 plus 8. So what's 4 plus 8? 12. I'm going to write a 2 down, and I'm going to carry the 1, right? Or I'm going to regroup the 1 because that's the tens place of the number 12. And then 1 plus 3 plus 1 is 5. Okay, it's efficient. I don't have a lot of writing involved. It moves through very quickly. So this is the standard algorithm. This is the one that people tend to gravitate toward. Even if they don't start with this one, this is the one people gravitate toward eventually because it's fastest to use. Okay, let me go back then and get my concrete model. So the concrete model is the place where you would start typically with children because you're trying to sort of help them to envision what it is that they're doing when they're doing these kinds of additions. So we talked about 34 as being 3 longs and 4 units. Nod your head if you remember that, okay? We did it, we even had a question about longs and units in our homework. So let me make that thinner. We're going to draw 3 longs, and we're going to draw 4 units. This is 34. Now, if you were doing this with children, would you be drawing on a piece of paper? Probably not. You'd probably get out something like my base 10 blocks, right? Or maybe you'd actually be using Legos where you stacked them together, or you'd have some base 10 blocks that actually click together. That'd be better than the static ones I have. But you'd probably do something concrete right? Tactile learning, right? Those kind of kids, right? And in fact, to some degree, all your kids are that kind of kid when they first start out, right? Touching is very visual. It's very stimulating. So it's a good place to start. The other one is 18. So we're going to draw one long, and we have 8 units. Okay, everybody good so far? And then what we're going to do is exactly what we did on that question that was asked. We're going to merge them all together. But we want to have as few blocks as possible. So what do you think we're going to do with all those little units?
Trade them out for long.
You're going to trade them out for long. Like you're going to like merge them all into the same pile, right? So if you wish, I'll actually do it. We're going to like stick them all over there together, right? Recollect them. And I'm going to find 10 of them. This is 10 of them. I don't want a box. I want a circle. Like this. There's 10 of them there, I think. Yeah. And I'm going to trade that out into a long. And if I had too many longs, I'd trade it into a flat. And if I had too many flats, I'd trade it into a block. I mean, I'd keep trading up. But at this point, that's enough, right? So then, how many longs do I have? 5. And how many units do I have? 2. And this justifies very well what's happening here. And in fact, if you start here with this picture and talk about what's happening, it gives a lot more context into what that 1 is doing up there. What is that 1 doing? Well, it's the regrouped long, right? I have the 2 that stayed in the units form, and I regrouped the 1 long into the long column, and the column with all the other longs in it. Kind of an in-between option is called expanded algorithm. So the expanded algorithm does sort of, it's a little bit more writing than the standard algorithm. Not a little bit more, it is more. But it gives a little bit more detail as to what we're doing. So we're going to write 34 as 3. Let me see how I wrote it in here. Yeah, as 30, and then plus 4. So we're breaking it apart by its place value. This is 30 plus 4, and I have 10 plus 8. Okay, everybody good so far? Okay, so you're welcome to still add from left to from right to left like we normally do, but you can also do this adding from left to right. So I could actually add down. This is 40, and this is 12, and it'll work okay. Now the kicker is that 12 would have to be regrouped or separated. It would have to be separated by its place value. Well, 12 is 10 and 2. Right? I'm breaking the 12 apart into its place value. That leaves me with 2 here, and then I have 40 and 10, which would be 50. So this is 52. So you can see the numbers breaking apart in such a way that we get to the same answer. All right, there's a couple more, a little less common, but there is some appeal to them for different reasons and for different learning styles. The next one's called column addition. I'm showing you a longer expansion of it because it works a little bit better, or maybe it makes more sense to use it when you're adding several digits together and not just 2 digits like the exact examples I did before, okay? So if I'm doing column addition, I'm still writing it out the same way I have on the other problems, okay, vertically. But what I'm going to do is this one specifically is designed to move from left to right. Like that's its purpose, okay? So we're going to start with the leftmost column. That's 1 and 3. This is 4. But I have 1,000 and 3,000 really, so this is 4,000. I'm adding the column that's the thousands together, and I get 4,000. So I'm going to write over here to the side what I've done, not because your kid would write this out, but because I want you looking back at it later to remember what we did. We added the thousands column together. And then we're going to add the hundreds column together. 5 and 2 is 7, so this is 700. Because we really added 500 and 200. Everybody good so far? Okay, so what would we do next?
So we'd add the 30 and the 10.
Yeah, so we'd add the tens column, which gives us 40. And you're right, that's 30 plus 10. And then the ones column happens to be the first time we get a double digit. It didn't have to be for the other ones, it just happens to be. And I have the number 12. So the last column is actually 4 plus 8. And then at the end of this, we're actually able to do the same thing, move from left to right, but in most cases, I don't have to add anything, right? The 4 is the only thing in the thousands column. The 7 is the only thing in the hundreds column. But then I have a 4 and a 1, that makes 5 in the tens column, and I have a 2 in the ones column, giving me 4,752. Okay, ready for the next one? Okay, the next one is called the lattice algorithm. It has a counterpart when we get to multiplication that's maybe even a little more helpful. But let me show you what this looks like, and it'll set the stage for what we do later on in a couple of days. So this is 1894 and 3218. I think those are the same numbers, no, different numbers we had before. What we're going to do is we're going to draw a rectangular grid underneath them. Center. And because I'm adding 4-digit numbers together, I need them to be 4 digits by 4 digits, okay? So I need them to have 4 spots down here. Okay, everybody good? And then we're going to cross hatch them. So we're going to go like this. This is why it's called a lattice, is because that's the design that you see. All right, now each of the numbers, again, this one is perfectly designed to work from right to left for the addition if you would like. We're going to add 3 plus 1, and we're going to get a 4, and we write it down here in this box right there. My box is too small. I'm going to make my box a little bit bigger. I'll make my numbers bigger too, just for fun. Okay, so this is a 4 down here. All right, so I've added the 3 and the 1 to give me a 4. 8 and 2 gives me 10. That's a 2-digit number, but that's why there's a split box. The tens, one goes in the top corner, and one's digit, which is a 0, goes in the bottom corner. The next one we have is another 10, so I've got 1 and 0. And then I have 4 and 8, which is 12, so I have 1 and 2. Okay, pretty good so far? Okay, so this is the individual addition or multiplications that we've had. And then what we do is we extend the lattice diagonals along, and we actually do now need to move from right to left. So in this corner, we only have a 2. In this one, we have 1 and 0, which is 1. Here is 1 and 0, which is 1. And here is 1 and 4, which is 5. And if you did have something that added up to too much, which is a possibility here, right? Like you could have gotten something where these two numbers add up to, say, 12. You'd write the 2 down and you would carry the 1. That is what you would do. Okay, that's lattice multiplication. Or addition, sorry. Let's do one more and we'll stop before scratch addition since we're running out of time. I have time for opposite change. Opposite change is the idea that there are some numbers that are easier to add together than others. So when I take 488 and I take 231, 488 is really pretty close to 500. Agreed? Okay, and it would be a lot nicer if it really were 500. Also true, right? We're going to do this step by step, and the way we do it is we look at the numbers at the end. I really am going to look at the 8 and the 1. Which one's closer to the next value up? And 8 is, right? So I'm going to add 2 to the 8. But if I add 2 to something, I have to compensate by subtracting 2. So you add a little, you have to subtract a little. So 488 will become 490. But what will 231 become? 229. Okay, 490, again, that 9 in the tens column, would be much nicer if I had 500. If I add 10 to this, that does that. And to compensate the opposite change that I'm doing, I need to subtract 10. So the 490 becomes 500. The 229 becomes 219. And then I can add, and I will get 719. The reason this is nice is because I get zeros somewhere. So somewhere along the way, I get it zeroed out. That's the goal, really, is that I've got it zeroed out except for that first digit. I don't end up with carrying involved or regrouping involved because I've got a lot of zeros involved. Okay? So we'll stop there for today.